Recorded.
So regarding our new prediction codes, to ensure that our model was capturing the most meaningful pattern in the data, I explicitly defined the categorical and numerical features in pie-carrots, setup functions. Categorical variables such as neighborhood group, neighborhood, and room type are processed to ensure the model to interpret them correctly. Meanwhile, numerical variable including latitude, longitude, minimum nights, and engineered features like host density and demand score was carefully selected to improve prediction accuracies. Feature engineering played a crucial role in boosting model performance as well as new features, how capture hidden trends and interaction with the data sets. Um, so Automated model selections, rather than manually selecting the regression algorithm, I utilize Packard's compare model functions, which systematically evaluates multiple regression model that ranks them based on mean square error, MSE. This data-driven approach ensures that the best performing model is chosen objectively. For the model comparison results, the light gradient boosting machine, Lights GBM, achieved the lowest MSE results 44,209.92 and the lowest RMSE, which is 204.13, making the most suitable choice for this data sets. Additionally, it has the highest R square score, 0.1879 among all models, indicating its ability to explain a greater proportion of the variance in the target variables. But the Humber regressor had the lowest mean absolute error, MAE 62.15. Its MSE and RNSE were the highest were higher than Light's GBM, and its R score are significantly lower. This suggests that while Humber was effective at reducing absolute errors, Light's GBM provides a more balanced trade-off between bias and variances. To further refine the chosen model, I employed automated hyperparameter tuning using PyCaret2 model functions, optimizing it based on MSE hyperparameter tuning, which allows me to adjust learning rates, tree depth, and future sampling strategies to improve generalizations, optimize boosting iterations to ensure convergence at the best possible error rates, prevents overfitting by fine-tuning regularization parameters. To ensure the consistent results across different runs, I set session ID equals 2025 within the setup functions by fixing the random seeds. I prevent variations that in train test splits, model initializations, and parameter search results. This guarantees that every execution of the pipeline yields identical outcomes, which is critical in research production environments, and deployment scenarios.
So for the accessing and refining the model fit, we first do a cross validation for generation. Uh, to ensure that the model was not overfitting to a particular dataset split, I employed k-fold cross validation, where the dataset is literally divided into training and validation subsets. So this approach provides me a more stable and reliable estimate of the model performance and give me more memorizing specific data points. So also I did the multi-metric performance analysis. Instead of evaluating model performance using a single metric, I analyzed multi evaluation criteria. For the first one is mean square error. It's second is the root mean square error, RMSE. Also the R square score, and also the mean absolute error, MAE. So by balance this metric, I ensure that the model was not only accurate but also consistent and interpretable. And to and Also I finalizing the model for deployment. Once tuning and validation were complete, I finalized the optimized model using finalized model and training it on the entire data set to maximize the predictive power.